Okay, hi everyone. My name is Jacqueline. I'm from Texas A&M University, and I'm going to be talking about a study called the ZFK2 survey. So this galaxy here was discovered in 2017, and it was exciting for two reasons. Number one, it's one of the most massive PSM galaxies discovered at high redshift, with a stellar mass of 10 to the 11 solar masses. And two, current cosmological simulations don't predict the existence of these things, and so they really challenge our understanding of how galaxies form and evolve. And so my work has to do with the first complete K-band exploration of massive galaxies at these redshifts. And we split the K-band into K blue and K red. And so this allows us to really beat down our systematic uncertainties and achieve less than 2% photometric redshift uncertainty. And so if you'd like to hear more about my work and the ZFK2 survey, just look for the lady in red and blue.
Ben Boisel, also from Texas A&M University. I think some of the rest of us are also there, sorry. My work is in precision black hole mass measurement using especially the ALMA telescope. This work builds on a lot of work from about 20 years ago with HSG observations of ionized gas disks. However, it uses more dynamically cold tracers, 12CO observations in nearby early type galaxies to be able to very well constrain the intergravitational potentials of these luminous galaxies. So here's just a just a sample of about half of these are rotation curves from our own galaxies, about the other half are from the ALMA archive, and some of which are going to be able to be used as very precise probes, percent level precision black hole mass measurements in some of these best cases where the gas approaches very close to the black hole sphere of influence and well within it. So if you want to come see my poster, I'd be welcome to, or happy to answer any questions.
Hello, I'm Sierra, and
I'm Ryan.
Unfortunately, Riley couldn't join us today. He's feeling unwell, but our research talks about the classification of sources in the HEPTEX database, and our sources go through 3 different types of classifications. The first being, is it real or fake? The second, if it's near or far, and then third, if it shows a line in alpha emission line or not.
So the problem with classification is that traditional programs can't really tell the difference between these two sources. One of them is Lyman alpha, the other one is O2. So often the work involves looking at these sources by eye, and that's really intensive work. So we're working on a way to automate this process, and to do that we need to build a robust learning set. And for more information on that, please check out our poster and the flyers here. We talk about the HEPTEX workshop, so please check that out.
Hello, my name is Jonathan Cohn. I'm a 4th year graduate student at Texas A&M University. Yes, I'm another one of those. So I look at gas dynamical mass measurements of supermassive black holes, and particularly the type of galaxies I look at are called compact elliptical galaxies. So the galaxy I'm measuring is UGC 2698 here. Compact elliptical galaxies are interesting because they're redshift 0 galaxies that look like relics of redshift 2 red nuggets. So we think that they've completely passively evolved since redshift 2. They've just happened to not merge with anything, which means their black holes haven't gotten bigger since redshift 2. They haven't really had anything feed them to change since redshift 2. So I use ALMA data, get gas dynamical mass measurements of the supermassive black hole at the center, and then we can start learning things maybe a little bit about what black holes might have looked like around redshift 2. So come and see my poster if you want to know more.
Hi, so my name is Zoe DeBurs. I'm a 4th year undergrad here at UT Austin studying physics and astronomy, and I've been working with Andrew Vanderberg since last fall. So my research focuses on significantly increasing the sensitivity of the radial velocity method by combining it with neural networks. So here are some highlights of some of my favorite plots that you can see on my poster as well. But essentially what we're doing is we're simulating data using a program developed by the CFA, and with that data we're simulating 20,000 different kinds of cross-correlation functions, which will look at regressing out the spots and pelagias of stars that will be hosting exoplanets. And so the idea is that if we can use a neural network to regress out this noise, we would be able to significantly enhance the sensitivity of the radial velocity method to Earth mass exoplanets. And over here, what you can see is for a simplified data set, we use a linear model to predict the radial velocity just looking at this cross-correlation function that you see in the upper left corner, and we see a pretty linear relationship between the true velocity and the predicted one, and that reaches a precision of about 1 millimeters per second. Obviously, that is not what we would expect with real data, but it shows that it could be a promising method for using spectrographic real data as well. Yes, thank you. Come check out my poster.
Hi, I'm Yasmin Devarkana from Texas A&M University. I am also doing black hole mass measurements. I just really showed them for us today. And so what we're doing is we're taking, measuring stellar kinematics of various galaxies at different radii, applying dynamical models to them for stellar orbits to measure the black hole masses. And we're looking at the correlation between the mass of black holes and the properties of the galaxies. Previous studies have preferentially selected galaxies within a certain range of galaxy parameters, mostly for ease of measurement. So we're trying to push that to a more robust range of galaxy parameters and properties to really explore that correlation between the supermassive black hole mass and the galaxy properties. And so I'm looking at LRS-2 data taken from the HT telescope, and my poster will show the kinematic information for one of the galaxies, galaxy number 7 in the sample. So if you want to see more about that, come see my poster.
Hi, my name is Mr. Carpenter. I'm a 5th-year graduate student at Texas A&M, and my work involves using deep HST GRISM data to constrain the stellar populations and assembly histories of massive quiescent galaxies from just about 1 to 2. My poster involves 2 projects. The first is a paper I released earlier this year where I focused solely on the G1-2 GRISM data from the CLEAR survey. And we measured the stellar populations for a sample of 31 galaxies, and we focused on the light-weighted ages and the metallicities. Here's an example of the GRISM data and the Bestman model. And the second project that I will be showing, we take the full data set, G102 GRISM data, G1 for 1, and the full photometry set, and fit with those non-parametric star formation histories, and taking these assembly histories and morphological results from Vanderbilt 2014, we begin to draw conclusions between the galaxy compactness and its formation redshift. So if you're interested in this, come see me, my poster.
Hi, I'm Sam Factor. I'm a graduate student at UT Austin, and I'm developing a direct imaging technique that allows the detection of companions at or below the diffraction limit of the telescope. And instead of using a more classical PSF subtraction technique, this technique interprets all of the little bumps and wiggles in the diffraction pattern as information about the source that is creating that diffraction pattern. To do this, I model the aperture of your telescope, in this case Hubble, as a grid of subapertures, and then simulate an interferometer with that geometry. And using this technique, it's possible to detect companions like this 63 milliarc second binary, which is at about 0.4 lambda over d at this wavelength. So I'm working on making this pipeline a readily accessible Python package, because I think it could have some very interesting applications outside of star and planet formation as well. So come and talk to me about that.
Hi, I'm Joseph Guidry. I'm a 3rd-year undergrad here at UT Austin, and I've been studying outbursting pulsating hydrogen atmosphere white dwarfs. You can see they're characteristically pretty similar in the ZZ study instability strip, but these stars, 2 known outbursts were observed simultaneously in Kepler's Campaign 16 and the Pan-STARRS survey. So that gave us the first multicolor photometry of these stars. And so we sought out to see this, or find an evolution of color to give us temperature information. And the results were a little inconclusive, but we're optimizing the analysis right now. And if you would like to hear more about that, please come see my poster. Thank you.
I'm Stephanie Ho. I'm a postdoc at Texas A&M. My research is focusing on the thermogalactic medium, which is the CGM. It is the diffuse gas around galaxies that extends to the Fourier radius. the CGM holds a better enriched gas flown away from the galaxies, also regulates the gas accretion on the galaxies. Therefore, the CGM plays an important role to the evolution of galaxies and the assembly of the galaxy disk. My research focuses on the CGM kinematics. I mainly use observations. I just place our sight lines to probe the inner CGM of selective foreground galaxies, and observe the CGM using the intervening circumgalactic absorption detected in the quasar spectrum. So the main result of my research is that the cool CGM, which is cool means 10 to the 4 Kelvin here, the cool gas in the CGM has significant angular momentum. Even for gases like tens of kiloparsecs away from the galaxy center, seems to know about how the galaxy disk is rotating, and it rotates with the galaxy disk. But the thing is that the gas is not rotating fast enough to be in a circular orbit, suggesting that the gas is spiraling towards the galaxy and eventually feeds the galaxy disk. To hear more about CGM kinematics in observations or in EVO simulation, feel free to talk to the others in my poster. Thank you.
Okay, hi everyone. My name is Tharni Kunchati. I'm a third-year grad student at Texas A&M, and I'm working to characterize Myra variables in the optical. So, Myras, specifically oxygen-rich Myras, have been used as extragalactic distance indicators owing to their low scatter period luminosity relations in the infrared and the near-infrared. However, the LSST is going to put us within reach of thousands of Myras across a very large volume of space. So it would be prudent to understand how Myras behave in the LSST bands. So to that end, I've been working with GRIS observations of M33 to recover a sample of known Myras and hopefully increase that sample as well. If you'd like to learn more, come by my poster.
Hi, I'm Rebecca Larson. I'm a PhD student here at UT, and I'm presenting a poster about the Keck program that I'm leading called Islands of Ionization. So this is searching for Lyman alpha emission at redshift 9 so that we can constrain potentially the sources of the ionization of the universe, and we can actually determine the volume of ionized medium in the universe at redshift 9. And so there's different theories, and potentially if one of them is correct, then the universe would be more ionized, and we'd actually be able to see Lyman alpha at this redshift instead of it getting attenuated by neutral IgM. And so we have 5 nights of Keck data taken. There's 2 more upcoming, and so if you want to hear about all the hoops we've had to jump through and improvements to the pipeline reduction to try to do redshift 9, right now with current telescopes, please come see me. We've done a couple extra things that the pipeline doesn't normally do, and potentially we have found Lyman alpha at redshift 8.7. And so there's some really interesting implications and then a nice coincidence. If you want to hear more about that, come find me at my poster.
Hi, I'm Catherine. I'm a first-year grad student here at UT Austin. I'm going to be presenting my undergraduate research, which involved the analysis of a newfound, very rare Wolf-Rayet type star in the LMC. So this star was found entirely by accident in a survey looking for quasars, and it belongs to the WC11 subclass of Wolf-Rayet type stars. The first member of the WC11 subclass was found in 1968, and since then fewer than 10 stars under this classification have been found. So this discovery is rather significant. This is also the first WC11 that is extragalactic. I present a spectrum, spectral energy distribution, proper motion, and photometry. And this object also hosts a planetary nebula, but curiously it's been missed by previous LMC, planetary nebula, and Wolf-Rayet surveys. So I suggest improvements for future surveys to find more of these objects. Thank you.
Hi, my name is Jessica Myron. I'm a senior physics major undergrad at Texas A&M University. And my project is how universal is the universal R process pattern. So I'm using a spectral synthesis, which is the black points here, and I have plotted a model over those, and I'm trying to derive abundances for these heavy R process elements. And then from these abundances, I'm plotting the log epsilon abundance versus the atomic number, and plotting against a known solar system pattern. And if you scale that up or down, I did it based on the average distance between the points. It actually kind of fits quite well, or kind of well. And so we're trying to find if this pattern actually matches non-enhanced stars in these heavy R process elements. Maybe they have an average of S process, slow, rapid, or rapid process. But yeah, if you want to learn more.
Cool. Okay. Hi, everybody. My name is Alex Riley, and I am a third-year graduate student at Texas A&M University. Normally, I study the dynamics of Milky Way satellites, and one of the key questions that comes from that field is whether or not the satellite galaxies, globular clusters, etc., are all following on this so-called vast polar structure. And so the idea is that if you sort of plot the direction of the angular momentum of all the Milky Way satellites, the classical ones which here are in green, and the stream normals, which here they're shown in red, they all seem to sort of cluster in a direction that is orthogonal to the direction of the Milky Way disk. And so the idea is that since this study came out in 2012, we've discovered a whole bunch of new Milky Way stellar streams, and things like the Dark Energy Survey and Gaia, and we also have new proper motions for all the globular clusters. And so the idea was, okay, given all this new and updated information, are things still clustered in a VPOS-like thing? And ultimately, you can come to my poster to find out, but the answer so far is, go to the next slide, probably not. So yeah, come talk to me if that sounds interesting.
So hi, I'm Maddie Lucy. I'm a graduate student here at UT. And my work is about selecting red clump stars from photometry, and so the goal of this project is really to create a complementary distance catalog to Gaia, because we know that red clump stars are going to provide better distances than Gaia parallaxes at distances greater than 3 kiloparsecs. And so the goal is to select red clump stars. It's shown that you can select red clump stars using the carbon to nitrogen ratio. And so this information should also be in the SEDs of these stars. So we create a 13-band SED by combining Gaia, 2-mass, all-ice, and pan-stars, along with parallax information, and use a mixture density network, which is a version of a neural network, to select these stars. And so we have a sample of 5 million, and there's the galactic distribution of these. This work was also done at the Kavli Summer Program in Astrophysics, so if you have questions about that, come talk to me. And I will not be here tomorrow during the poster session, so come talk to me today.
Okay, let's hear it for all the poster presenters.